Last lesson we looked at translations. Today we'll include dilations and reflections. We've seen these a little before, but let's up the ante a little bit now that we're in year 11. So what we've got to the right here is a function f of x equals x, the most basic linear function. That's that function there. And the function y equals x is dilated by a factor of 2 from the x-axis. Okay, now what that does is form this new function, y equals 2x. Now, if we consider the mapping here, here's a point on the original function, and that point is 1, 1. And what happens after we do the transformation, the dilation by factor 2 from the x-axis, is the point becomes 1, 2. Now notice here that the x value stays exactly the same, and the y value is the one that gets multiplied by 2 or dilated by a factor of 2. The y value has been dilated by a factor of 2 multiplied by 2, and this is the really important conclusion, and I say this all the time when I'm doing transformations. Dilations from the x-axis change the y values. Okay, and you can note to yourself the x values stay the same. So more generally, the mapping is x comma y maps to x stays the same, y gets multiplied by 2 to do a dilation by a factor of 2 from the x-axis. So show using mapping that when the function y equals x is dilated by a factor of 2 from the x-axis, this is our new equation. Right, so we're going to go x, y maps to x, that doesn't change, and we're doing a dilation factor 2 from the x-axis, which changes the y value. Now recall that what we do is we write x dash and y dash up the top there, and note that x dash is x and y dash is 2y. Okay, so now what we're going to have to do is look at our original function, okay, which is this. That is in terms of y and x. So this one doesn't need to be transposed, but this one here, we're going to go y equals y dash on 2. Right, now let's make our new function. So this was our old one, so we're going to make our substitutions. That's going to be y dash on 2 equals x dash. And let's make y the subject. Y dash equals 2x dash, and now let's make a function of its own, y equals 2x. Okay, and that's our new function. So let's have a look at another one. We can also dilate from the y-axis. So notice that before what we did was dilated from the x, what we can do is go from the y. So notice here that this coordinate point 2, 2 here becomes the coordinate point 4, 2 after a dilation by factor 2 from the y-axis. Okay, so again, note that we started with 2, 2, it became 4, 2, and what we were doing is dilating from the y-axis. Now notice here that what happens is the y values stay exactly the same, still 2, but what happens to the x values is it gets multiplied by 2. So here's the conclusion, dilations from the y-axis change the x values, and this is the mapping. So find the equation of the image obtained when y equals x is dilated by a factor of 2 from the y-axis. Right, that one is a little bit harder to guess and check, but let's do it. X comma y maps to 2x comma y, x dash and y dash. All right, let's write it out. X dash equals 2x, y dash equals y. Our original function is y equals x, so I need to get make y the subject and x the subject. So x dash over 2 equals x, and don't need to worry about this. Okay, now we're ready to make the substitution. So I've got y dash for y, x dash on 2 for x. Now let's write a function, write it as a function on its own, y equals x on 2. So this new function here, if I want to dilate it by a factor of 2 from the y-axis, forms the function y equals x on 2. Now you might note that this same transformation, so before anyone asks, the same transformation can occur by performing a dilation of y equals x by a factor of half from the x-axis, and you'll find that different sets of transformations can produce the same overall transformation. So if the question in the exam said, if this is a function here, y equals x, and this is the new function, the new mystery function, what transformation could happen to y equals x to turn it into this? You could say that it would be a dilation by factor 2 from y, but you could also say that it's a dilation factor half from x. Both of them would be equally correct. Write down the equation of the image obtained when the graph of y equals 1 on x squared, this truncus, by a factor of 4 from the x-axis. All right, so see if you can guess and check this. I'm going to write it up. Maybe pause the video and see if you can work it out by kind of recognition. So that's what I think the answer is by recognition. So I think it's going to be 4 on x squared. So it's going to be x comma y. Now why do I know that? Because I kind of think about this like a parabola maybe. So if you've got y equals x squared as a parabola and I want to dilate that by factor 2 from the x-axis, I slam a 2 out the front. And so this one here, what I think about is this is y equals 1 on x squared, which is y equals a dilation factor from x times 1 on x squared. They want the dilation factor to be 4, so I'm going to go y equals 4 times 1 on x squared, which is y equals 4 on x squared. Anyway, if you're not too sure about that, mapping will do all of the work for you. So dilations from the x-axis change y. X stays the same. X dash is equal to x, y dash is equal to 4y. This is the one I need to play around with, and I need to make y the subject to slam it into the original function. Y equals y dash on 4. Right, let's make the substitution. Y dash on 4 equals 1 over x dash all squared. All right, let's multiply by 4. Y dash equals 4 over x dash all squared, or y equals 4 on x squared. So pretty easy. Dilated by factor 4 from the y-axis. Okay, so if this is our original function, pause the video and see if you can think about what this function might look like after a dilation factor 4 from the y-axis. Right, if you've unpaused it now and had a go at it, okay, the answer is going to be, I think, so we'll see, because I'm not too sure about this one, but I think it's 1 over 16x squared, I think. And if you guess that one, you're going pretty well. Okay, so this is the first instance where I'd say to you that to do this problem here, you really need to do mapping. So x comma y maps to, now this is dilation by factor 4 from y, so it changes the x value by a factor of 4. Y stays the same. All right, so now what we're going to do is x dash equals 4x, y dash equals y. All right, x is equal to x dash on 4. Don't need to mess around with that one. Right, so now, see, I've got that wrong. So that is wrong. I already know it's wrong, and this is fantastic because it's great for you to see this happen. All right, so I'm going to substitute not into that one, but note that that's my original function. So I'm going to put y dash on for y, 1 over x dash on 4 all squared. All right, that's equal to y dash equals 1 divided by x dash all squared over 16. Now what's going to happen is multiply by the reciprocal and all. 16 over x squared equals y. What I'm going to do is just drop the dashes straight away to form my new function. So I was close with the 16 but put it in the wrong spot, and actually I shouldn't be saying things like that was close, because that is wrong and that is right, and they're two completely different things. One is a dilation factor 1/16 from x. This is a dilation factor 16 from x, and if I'm claiming that they're close, I must be crazy. All right, so there it is there. So dilation by factor 4 from the y-axis would look like this, but also dilating by a factor of 16 from x would yield exactly the same results. Okay, as with dilations rather, reflections can also be counterintuitive, or I believe they are counterintuitive. So the graph of y equals root x has been reflected in the x-axis. Okay, so here's our original function, y equals root x. You can see here the reflection in the x-axis. Now note the coordinates here. We've taken this point here, 4, 2, and it's become 4, negative 2. And notice that when we've reflected in the x-axis, notice how x is the same, 4 and 4. What's changed? Well, a negative sign has been dropped in front of the y value. So that's the same, that's opposing signs. So more generally, the mapping it works like this. X comma y maps to, X doesn't change, and we slap a negative sign in front of that Y value to reflect it in X. So reflections in the X-axis change the Y values. So think dilations as well. It's exactly the same as dilations. So state the equation of the image obtained when y equals root x is reflected in the x-axis. Now hopefully you know by recognition or by our prior work that it's that, but just say like, oh, I don't have a clue, no idea. So jam it into the mapping. So reflections in the x-axis change y. X dash equals x, y dash equals negative y. All right, now I need to make y the subject over here, so I'm going to go y equals negative y dash. All right, so now I'm going to rewrite my function based on the original being this. So I've got negative y dash equals root x dash. Now I'm going to divide both sides by negative 1. Y dash equals negative, x dash, y equals negative root x. So again, that's one that you can do by recognition, and I hope you do that one by recognition. But again, there's going to be instances where we do, particularly reflections from y, that are important that we can use this mapping technique. So graphs can also be reflected in the y-axis. Here's root x here, and if it's reflected in the y-axis, notice what happens here. So this is 4, 2, and look at what's changed. Reflections in y change the x or negate the x, the y stays the same. Reflections in y negate the x, y stays the same. So reflections in the y-axis change the x values. Now, state the equation of the image obtained when this is reflected in the y-axis. Well, I believe the answer is going to be y equals root negative x. But just say you were like, would not have a clue, Mr. Miller, I don't know what it's going to look like. Map it. Okay, x dash equals negative x, y dash equals y. All right, that's going to mean that x equals negative x dash, and now we're ready to substitute. Oops, I put power 2, negative x dash. All right, so that's my original function there. So y dash goes on, root negative x dash, or y equals root negative x. All right, so what many tutors will say is something like Dr. T, okay, as a way of remembering transformations. Dr. T means that's dilations, that's reflections, and that's translations. Okay, speaking of dilations here, dilations, make sure you note how it's spelt. So it's dilations. I just, again, had probably a couple of kids a few years ago in my class write it as dilations, so dilations. And maybe it's because of the way I said it. It was written down correctly everywhere, but they've heard me say it a fair few times. So it's a dilation, not dilation. Okay, so practice that word at home. You should be hopefully at your desk at the moment just repeating the word dilation, 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 and someone who walks past you at this point is probably going to think you're going slightly around the bend. Okay, so when we perform transformations, girls, I'm afraid you've got to do it as you're told. Okay, that's very important. So don't take artistic liberty, or don't be like, I always do dilations first, I always do reflections second, and I always do translations third, because my tutor said use Dr. T. Okay, so it's really important that if we ask you to do a transformation and we list the transformations, you've got to do it in that order. Now, what am I banging on about? Well, let's do an example. Give the equation of y equals root x after the two transformations are applied in the order given. Translation 3 units in the positive direction of the x-axis, followed by a dilation factor 2 from the y-axis, followed by a dilation factor 3 from the x-axis. All right, let's set this up. Starting with x comma y, let's do the first one, translation 3 units in the positive direction of the x-axis. That, we recall, is just doing that. Okay, adding 3 units to all x values, the y value stays the same. Followed by dilation factor 2 from the y-axis. Okay, so dilations from the y-axis change the x value. So we're going to go 2 brackets x plus 3. So this basically translates first and then dilates the results. That's what's going to happen in terms of my order of ops there. Nothing happened to the y yet, followed by a dilation factor 3 from the x-axis. So dilations from the x-axis change the y value. So I've got 2 x plus 3, comma, what is it, 3? Yeah, 3, y. All right, that's x dash, and this is y dash. X dash equals 2 x plus 3, y dash equals 3y. All right, so now what I'm going to do is make x the subject and y the subject so that I can sub it into this to make my new function. Now note at this point you could expand that and then transpose it, but I'm not going to do that. Okay, I'm going to say that x dash on 2 take 3 equals x and y dash on 3 equals y. Now if you expanded that and then transposed it, your expression is going to look slightly different to mine, and that is okay. That is okay. So it's very important to note that if it's algebraically true, then you can do it. Okay, you might then get a different set of transformations, or the transformation order might be a little different, but ultimately you'll be correct. Okay, all right, let's see it. So now what we're going to do is form our new function. So y is y dash on 3 equals, now under the root sign is x dash on 2 take 3. Now what we're going to do is multiply it by 3, so y equals 3 root x on 2 take 3. Just make sure that square root sign goes all the way down and all the way across. Apparently the 3-4 exam at the moment, they're dynamite on square root signs, so make sure it covers exactly what you want to be square rooting. Right, so there it is. So if you can see that by recognition and actually generate that without any of the mapping, that's pretty good. Okay, but the mapping just throws out what the final function is going to be. All right. So now we've got a dilation factor 2 from the y-axis, followed by a translation of 3 units in the positive direction of the x-axis, followed by a reflection in the y-axis, followed by, there's bucket loads going on. So again, if you can think that through and write the function after all of those things, that's fantastic, but I've got no chance. So dilation factor 2 from the y-axis. That changes the x values, followed by translation 3 units in the positive direction of the x-axis. Followed by a reflection in the y-axis. So reflections in the y-axis change x. So it negates whatever's going on there. You could bracket that, but that negative sign out the front will be fine for that. Actually, no, we do need to bracket that. So it's negative all of this stuff here, which is the dilation and the translation. So you've got to drop a negative sign out the front of that. Reflection in the y-axis, followed by dilation factor 3 from x, 3y. So reflections or dilations in the x-axis change y. Okay, we're good to go. X dash, y dash. Notice procedurally it's exactly the same as all those other questions we're doing. So x dash equals negative 2x plus 3, y dash equals 3y, y equals y dash on 3. Let's do this one here. Again, you've got the choice of expanding or passing the negative across the two terms and then transposing. I'm not going to do that. So all I'm going to do is say x dash over negative 1, take 3, and then it's all divided by 2 equals x. And I'm just going to tidy this up a bit. So this is going to be like negative x dash, take 3 all over 2 equals x. Again, you can do whatever you want here as long as it's algebraically true. You can take out the negative and rewrite it if you want. I'm just going to leave it like that and make the substitution. So recall our original function was y equals root x. This is the stuff we want done to it. Okay, again, This is like the prescription. This is like me going into the hairdresser and going, right, here's what I want. Like, I want, half a centimeter taken off the top. That's unlikely. I want bleach blonde hair. I want then yellow, green streaks put around the bleach. Okay, that's all the stuff that we want done. So it takes the original, does that stuff, and produces the result. So this is the stuff that we want done. And now it's time to get the finished product. So y dash on 3 equals negative x take 3, and negative x dash take 3 on 2, all being square rooted. All right, let's multiply by 3 and drop the dash. 3 root negative x take 3 all over 2. All right, so there's our new function there that will have all of those transformations. What I'm going to finish off this transformation lesson in, or this transformation lesson, is this concept called transformations by equation. Okay, so this is a commonly taught method to do transformations. In fact, again, when I was at another school, this is the only method was used, and it was a rote-learn method, really completely rote-learned. All right, so if you want to do a transformation, and this one here, what this one here is a reflection in the y-axis, okay? So if you take a function f of x and drop negative x into the function, what you're going to do is cause a reflection to happen, okay? Best way to see that is if we do, or start with a function y equals f of x equals root x. If I do f of negative x, it's equal to root negative x, which is basically the root x function, like this, going to that. Okay, so this thing here, we're going to say that that is a reflection in the y-axis. There it is there. Now notice I use the word ref for reflection. It's okay as you're going about your business in workbooks, but again, if you're in an exam or in an assessment situation, you need to actually state the transformation. So it needs to be reflection. You need to use that full word. Right, this one here, what that's going to do is drop a negative sign in front of it. Well, let's think about another function, y equals f of x equals x squared. If I do negative f of x, what that's going to do is take whatever f of x is and stick a negative sign out the front of it, which is negative x. There's the original, turning at 0, 0, and negative x squared is just that one there. So this thing here, by doing this, what we're going to do is get a reflection in the x-axis. All right, this one here, what this is just say I had a function like y equals f of x equals, say, let's go x squared again, and I do 2 f of x. That means that whatever f of x is, can you please multiply it by 2? And notice that this is like the a value or the dilation from x. So this is a dilation to from x-axis. All right, this one's tricky. All right, so this one here, what we're going to do is actually throw some mapping at this, okay? So what we're going to do is say that, how are we going to do this one actually? Okay, for this one here, we're going to use a special technique to throw the mapping out. Now, again, I know by recognition that this is a dilation factor 2 from the y-axis. Okay, now how do I know that? Well, again, it's practice, but it's also this knowledge. So if I started with the function y equals f of x, and I'm moving to this new function here, y equals f of x on 2, what I'm going to call this is the original function, okay, and this is the image function. Okay, so now what I'm going to do is, I call this process here pairing up. So I've got y dash is equal to y, and x is equal to x dash on 2. All right, now what I want to do is work out the mapping that would take the function y equals f of x and create this new function. Well, what's it going to be? It's going to look like this. It would have started at x comma y, and remember that the mapping maps to this. So in this case here, what I'm going to do, girls, is actually solve this for x dash. Okay, notice how it's solved for x at the moment. I'm going to solve it for x dash, which is actually 2x equals x dash. Okay, now I'm going to write what x dash is, which is 2x. And I'm going to pop in y over here, which is what y dash is. Now notice what this is. If this was the mapping here, x comma y maps to these new image points here. This one here is 2x, okay, and we're multiplying the x values by 2. That means that this is a dilation to from y-axis. Now, what I taught at that school that didn't use mapping is, this is how I had to do it. I said that the dilation, okay, to work out a dilation from this point here, you do 1 on n, okay, where n is the coefficient of x. All right, so what does that mean? So the coefficient in this case is a half. So it's 1 over a half. That means a half goes into 1 2 times, and that's our dilation factor. The question for you girls, what would that dilation be? So if I do f of 2x, what would it be? Pause the video and have a think about it and tell me what you think. All right, well, by this formula here, if you used it, it would be 1 on the n value. Our n value is 2. That means it would be a dilation half from y. Okay, so this one here is a dilation factor half from the y-axis. This one here is a dilation factor 2 from the y-axis. Very difficult to understand at this stage of the game, but important to point out at this early stage. All right, here's another one here. So if you've got a function and you want to move it left or right, these are two, and up or down, these are two methods to use. So this one here, I'm going to use, or think about this one as a function again, y equals f of x, and then I'm going to do y equals f of x equals, say, x squared. And then I'm going to do f of x take 2. That means drop x take 2 into the function. All right, what does this do? Well, that's the parabola that goes through the origin. That parabola there is the original parabola moved 2 units to the right. So this is a translation 2 units right, or the positive direction of the x-axis if you want. Okay, this final one here, y equals f of x plus 4, that is a translation 4 units up. How do I know? Y equals f of x equals x squared. I'm going to do f of x plus 4, and that basically says whatever f of x is, chuck 4 on the end, please. That's f of x plus 4. There's our original function going through the origin. This sends the function 4 units up, or changes that turning point, i.e. translation 4 units up. This is a combined one. Okay, so again, if you're understanding what's going on here, hopefully you'll say this is a translation 3 units left and translation 2 units down. Now, how do I know? Again, think about y equals f of x equals x squared, and we're going to do f of x plus 3 take 2, which would be x plus 3 all squared take 2. And think about our two functions. There's our original. This one here, 3 to the left, 2 down. All right, so notice that our original function has been shifted 3 units to the left and 2 units down. 3 units to the left, 2 units down. Okay, again, these are really easy ways to shift functions around, is by simply dropping x plus 3 into the function. You'll create your new function. Now that can be really handy down the track. All right, if f of x equals 1 on x, determine the equation of the image under the following transformations. So here we go, we're doing this. So we're going to simply drop x plus 3 into it and then remove 1. So let's do it. So I'm going to say that we're going to create a new function. Let's call it g of x equals 1 over x plus 3. So wherever I see the x, I change it to an x plus 3, take 1. Okay, so i.e. it's going to move the hyperbola 3 units to the left and 1 unit down. Okay, this one here, what we're going to do is shift it 1 unit to the left, multiply by 2, and then subtract 4 from the result. All right, so we're going to say that a new function g of x is created by doing 2 lots of 1 over x plus 1, take 4, which is equal to 2 over x plus 1, take 4. Okay, dilated by a factor of 5 from the x-axis, dilated by a factor of 2 from the y-axis, reflected, translated, translated. All right, so what I want you to do is finish off this lesson by doing this or attempting it 2 ways. The first method is by mapping, the second method is by equation. Okay, so what I want you to do is pause the video now, okay, and once you've done it by mapping first of all, unpause it, and then we're going to try and do the same thing by equation. All right, so here is the mapping version. So what we're going to do is start with x comma y, dilated by a factor of 5 from the x-axis changes the y value. X stays the same. Then we're going to do this one, dilated by a factor of 2 from the y-axis changes the x, reflected in the y-axis changes the x, translated 3 units in the positive direction of the x-axis, we're going to get negative 2x plus 5. Whoopsie. I'm just going to be a bit bold here and do this in the same one. So translated 3 units in the negative direction of the x-axis, I'm going to go 5y, take 3. All right, this is x dash, this is y dash. X dash equals negative 2x plus 5. Y dash is equal to 5y take 3. All right, now let's make y the subject by doing y dash plus 3 on 5. I think that's right. This one here is going to be x equals x dash take 5 all over negative 2. All right, our original function was y equals 1 on x. And what we got was y dash plus 3 on 5 equals 1 over x dash take 5 all over negative 2. All right, now we've got y dash plus 3 on 5 equals, now what's going to happen is when I divide 1 by all of this, that's going to be a reciprocal. So we're going to go negative 2 over x take 5. Still got the dash there. I'm going to multiply by 5. Okay, so I'm going to go, and I'm going to drop the dashes at this point. I'm going to say y plus 3 equals negative 10 over x take 5. And then I've got y equals negative 10 over x take 5 take 3. So there is the version via mapping. Okay, so that's not easy by mapping. Right, but let's do it by equation and see how we go. So again, it's your turn to have a go by equation. Right, so pause the video and see if you can develop the equation, and then let's check it out. All right, so dilated by a factor of 5 from the x-axis. So what that's going to be, if we start with f of x, dilations by a factor of 5 is going to be 5 f of x. Then what we're going to do is dilate by a factor of 2 from the y. So that's going to be y equals x on 2. Okay. We're going to reflect in the y-axis. So that's going to be 5 f of x on 2. Translated 5 units in the positive direction of the x-axis. Here's where all the mistakes happen at this point here. So translated 5 units in the positive direction of the x-axis. Here's what many students will do. The positive direction of the x-axis, they'll write take 5. Okay, and that's wrong. Okay, so worth writing down that that's the issue. Okay, here's the correct one. Right, so what we've got to do to translate 5 units in the positive direction of the x-axis, we've got to do 5 or f of x take 5. That's what we've got to drop into the function. This is the function at this point here. And so what we've got to do is actually write it like this. Negative x take 5 in brackets. So where I see x, I replace it with x take 5 all over 2. Okay, and then finally translated 3 units in that. That's easy enough. Negative x take 5 on 2, close brackets, plus take 3. All right. So now what we're going to go ahead and do is do all of this stuff to the function. Recall that the function is f of x equals 1 on x. All right, so that means that I'm going to multiply it by 5. So I'm going to say that g of x equals 5. This is getting tough. I mean, I've got to substitute this in for x now. 5 over negative x take 5 in brackets all over 2 take 3. All right, now you see what will happen here. We're going to get that 2 there. When I divide by the reciprocal, that's going to jump up to there, and so will the negative sign as well. So g of x equals negative 10 over x take 5 take 3, which is exactly the same as that one there. Now, I dare say that took me a little bit more time than the mapping, okay? So again, I'm a real stickler for using mapping. Many teachers of this subject prefer this method here. You need to use both and you need to understand both. But there you go. There's 2 different variations on that problem. So after a fairly long video, girls, the exercises aren't particularly long. So give them a good go, and I would stick with the mapping predominantly at the moment.